In this video, I'd like to talk about SHViT, or Single Head Vision Transformer with Memory Efficient Macro Design from CVPR2024 that proposes a new type of vision transformer that can beat all the other models in a speed-accuracy trade-off. So let's just talk about it. But before talking about this paper, I expect you to know how vision transformers work. If you don't know, check out the video I have. But if you know how these vision transformers work, then you know that one of the issues they have is that they lack inductive bias. And that issue leads them to be data hungry. They need a lot of data to be trained. And the other issue they have is that they have quadratic complexity in both memory and computation. And researchers focusing on the second issue just to make it faster while being accurate. And the previous attempts can be divided into two different categories. In one category that we can call it macro design, like this FastViT paper from CVPR2024, they try to integrate different type of modules that we already have so as to make it more efficient. Like in this FastViT paper, they use something called linear train time overparameterization that you can even see on this figure, that on the training we have more branches and more parameters compared to the inference time, and somehow it helps. But the thing that we should understand from macro design is that we change how we integrate different modules and create the neural network that is more efficient. But in the other category, which is micro design, like Efficient Transformer version 2, again from CVPR2024, they try to go inside the transformer module and solve the issue. What's the issue? The multi self-attention that has quadratic complexity, right? So you can see from the figure on the left, that's the Efficient Transformer version 1, that what it tries to do is that you see that for the first stage, they replace the multi-self-attention with pooling. And they do the same thing for stage 2 and stage 3, with the difference that the patch size is different. And on the last stage, they use multi-self-attention. And in Efficient Transformer version 2, they propose another solution. Like you see this pooling, they replace it with depthwise convolution. And you see this multi-self-attention here, they replace it with this thing here. But I'm not going to talk about the details because that's not what we are here for. But one thing that we should know is that in micro design, they go inside the transformer and they try to modify things. So I hope we are all on the same page. Now let's just talk about this paper, the single head vision transformer. In fact, this paper uses both type of designs just to make it more efficient. In macro design analysis, they performed one interesting experiment. They picked an image and they patchify it with different patch sizes. Like for the first image, they patchify it by 4x4 patch embedding, and for the second one, they patchify it by 16x16 patch embedding. So we have larger patches, meaning that we have less tokens. And for the first design, they use 4 stages, with the difference that the first stage uses 4x4 patches, the second stage is merges the tokens, and it becomes 8x8, and then 16x16, and finally 32x32. In the second design, they use 3 stages, and they start by 16x16, and then 32x32, and finally 64x64. Now let's just see which one performs best. I guess you already know, right? The one that uses 4x4 patch embedding has more tokens, it has more attention to the detail, so we are expected that one to behave best. And that's actually true. But the one thing that we should also know is that out of all these 4 stages, the first stage is the actual bottleneck. Because let's just say the input image is having a size like 224 by 224. If I patchify it by 4x4 patches, that means I have 56 tokens on the height and 56 tokens on the width. And if I multiply them together, I have around 3000 tokens. But for the second stage, if I use 8x8, that means I have 28 on the height and 28 by the width, and multiply them together, I have around 700. So on second stage, I have around 4 times less tokens. So second stage should be much less computationally expensive compared to the first one, especially because of the quadratic complexity that we already have in the attention module. But one thing that I also need you to know is that You see that some of the stages are in blue while the others are in kind of red, as the others say. What is the difference? The difference is that they are all using a concept called metaformer, which I already have a video about it. But in a nutshell, what metaformer does is that it says you can simply grab the multi-self attention and replace it by anything. So in this stage 1 and stage 2, that they are denoted by blue, and also stage 1 on the second design, they grab the multi-self attention and replace it with depthwise convolution. Engineering wise, it makes sense because we are trying to make it faster, but theory wise, why out of all of these designs like pooling and other things, why we choose depthwise convolution, I'm going to talk about it later. But okay, these are the two designs that we have. Let's just see what happens. For the first design, if I use 24 channels on the first stage and I repeat it only once, 48 channels for the second one, 184 channels for the third one, and I repeat it 4 times, and finally 368 channels for the last stage and I repeat it 2 times, then with the input resolution of 224, I have around 4.9 million parameters, and you see the throughput on the CPU and GPU. Even on CPU, it is kind of fast, right? We can process around 430 images per second, and with GPU, it is around 11,000. It is already fast, and we can see the top 1 accuracy is 75%. But what about the second design? With second design, you see that the throughput on CPU is 2.8 times faster, on GPU it is 3 times faster, but the top 1 accuracy is 1.5% worse. And some people might say 1.5% is a lot. I cannot accept that. Even though it is making me to be 3 times faster, I don't accept 1.5% drop in accuracy. But let's just increase the resolution from 224 to something higher like 256. And simply by doing it, now we are 2.5 times faster than baseline, the first design I mean, but the accuracy is only 0.1% worse. So that's the thing that we can understand from this macro design analysis, that we have a lot of spatial redundancy in the first stages. And the way that we can tackle it is just by using higher patch sizes like 16 by 16, but instead increase the resolution from 224 to 256. And that's all we need. We are having faster model, but only 0.5% decrease in accuracy. So okay, that was interesting thing to know. But you all might also wonder, for the second design that I'm using 16 by 16 patch size, it is the same thing that the vanilla vision transformer is using. Why we are using depthwise convolution? Because for the first stage it kind of makes sense. I have around 3000 tokens, that's a lot. I cannot fit it in the memory perhaps, so I can use depthwise convolution instead. But what about the second one? What happens if I replace the stage 1 instead of this depthwise convolution with the multi-self attention? They have done it also, and you can see that comparing this last row with the second row, the performance is 0.5% better, but it is slower. But the thing is, if I just keep it as is, as the depthwise convolution for the first stage, but increase the resolution to 256, I have something that's not only faster, but is also 0.9%, almost a percent more accurate. So okay, so that's the thing about macro design analysis. They're also interested in micro design analysis, so let's just talk about that. So in micro design, they picked DIT Tiny, one of the vision transformer variants, and they visualized the self-attention map for all the layers. Like you can see here for the first 7 layers. And they also took the head similarities, which is the cosine similarities between the heads. And they also measured how much deduction in performance I have if I remove only one head or remove all of them except once. But note that if I want to do it, it doesn't mean that I have to train it from the beginning. I can train it only once, and for, let's just say, removing one head, I just need to nullify the output of one attention head. And by nullifying, I mean just multiply it by 0, just zero them out. And the interesting thing that we can see from this micro design is that for the first 7 layers, if I remove everything except one, I have sometimes 4.5% drop in accuracy. In some layers it is less, like here it is 0.5%, but it's usually more than 1%. And the interesting thing is that they picked the attention heads that they are most important, and they denoted by this red border, and the most redundant ones with this blue border. And you can see that the most important ones for the initial layers, like this one, or this one, or this one, they're all trying to extract local information. So that's probably the reason why they replace it with depth-wise convolution, because depth-wise convolution is what is good for extracting local information, right? And the most redundant ones, like this one, or this one, or this one, they're all trying to extract global information. So one thing that we can understand is that for the first 7 layers, all the important heads are extracting local informations, and the redundant ones are trying to extract the global information. And the heads are not very similar, but if you look at the deeper layers, we see another trend. Now we see that the heads are very similar. Like we can see that here there is 91% similarity between them. And now they're all trying to extract global information. So that's an interesting thing, that for the first few layers, it tries to extract local information, then it tries to extract global information. And now we can see that if we just remove everything except one, sometimes like the last layer, it's only 0.5% deduction in the performance. It is still sometimes more than 1%, but in average, it is less than the first 7 layers. So I believe that's the thing that inspired the others to say that we can probably use single head attention for the deeper layers, because in deeper layers we are having a lot of similarity between the heads. It's kind of, there are a lot of redundancy, and if we remove some of them, the performance doesn't decrease much. So we can kind of replace it with a single head just to make it faster, with a tiny bit of drop in the accuracy. And we can see the similar trend for swing transformer as well. They have picked the swing tiny, and we see that as we go deeper and deeper, the average cosine similarity will become higher. And what happens if I mask one head or all except one? You see that for the red one is the actual original performance, and the blue one is for the case that I mask only one head. And interestingly, in deep layers like this one, the performance becomes a bit better when I mask a single head. That's a strange thing. They didn't explain it why, but it was also surprising for the others. But the other thing that we can see is that for masking all except one, this cyan color, we see that for the deep layers, like from depth 6 to 10, the performance drop is not much. But for the early layers, it reduces the accuracy a lot. So that's one of the things that is kind of inspiring others to use single head attention in deep layers. So okay, it's enough about this analysis. Now let's just talk about how we can design a new neural network. So the first thing to talk about is that how they come up with the new block of the transformer in the micro design. They said, let's just say I have a feature volume like this, and select the first R portion of it and denote it by RC, and the remaining part as 1 minus R times C. And they set this R to be 1 divided by 4.67. So around 20% of the channels they selected, and then they pass this 20% to layer norm and self-attention, and then they come up with some new feature volume. But what they do with the remaining 80% of the channels, they just simply pass it to the identity operation, basically means do nothing with it, and have this remaining 80%. But when we do not do anything with it, that means we are not propagating any information from the result of self-attention to those channels. So to propagate this new extracted information to those channels, they concatenate these two together. And then they pass it to an output projection, which just kind of tries to propagate the information from this 20% to those 80%. We can just visually see from this color coding that they have done for the paper that you see now it is somewhere between yellow and blue. But you might kind of wonder why they have done this. They didn't really explain it why, but I believe that they came up with this idea after reading FasterNet paper from CVPR2023, that it actually does the exact same thing, but instead of using self-attention, it uses convolution. So you see the FasterNet block here, that is a kind of a metaformer block that replaces multi-self-attention with pconv. And pconv is partial convolution that you can see here. It is kind of the same thing. It selects the first portion, CP, and does the convolution for them. And for the remaining part, it does the identity. And just to propagate the information again, they use these one-by-one convolutions after that. So this is kind of the same idea. But why FasterNet have done this thing? They say, actually they visualize it with this figure, and they say when we visualize the intermediate layers of pre-trained resonant 50, we can see that lots of the channels are kind of redundant, like this one and this one, that they are all conveying the same information. And since we have a lot of redundancies, we can apply the convolution on a subset of them, not only all of them. And yeah, that's one reason. And the other thing is that they have realized that reducing flops doesn't necessarily mean that we are faster. And the real bottleneck is the memory I/O, that we need to read from the memory and write on the memory. And they theoretically showed that in depth-wise convolutions, even though they have less flops, they have more width, and having more width, that means that I need to have more read and write from the memory, and that makes them actually slower. So they propose this thing just to apply convolution on the subset of them instead of all of them, and they show that it actually becomes faster. So that's one interesting thing to know. But in single head vision transformer, they ran some experiments instead of theoretically proving it, and they show that we have a lot of memory bound operations that makes it slow. So they picked the small portion of it instead of all of it. Okay, so knowing about this micro design, now let's just talk about the macro design. So in macro design, we have to come up with integration of different modules. And they say once we have the input, we use 16 by 16 overlap patch embedding instead of the usual 16 by 16 patch embedding. And what that means is that we are using 4 3x3 strided convolutions. And then we have this first stage that is just simply a depth-wise convolution. I already gave you the reason why. And once we do it, we downsample it. So instead of 16 by 16 patches, we have 32 by 32 patches. And for the second stage, and also for the third stage, we use this architecture instead. That after the stepwise convolution, now we have single head attention, which is the same thing that I just mentioned. But to be honest, when I read this, I was kind of wondered why they have started using the single head attention from the middle and they didn't do it for the last one instead. But I guess that's probably because of the speed accuracy trade-off, and they realized that we can even do it from the middle, and that of course makes it faster but doesn't reduce the accuracy much, and they can still beat the other models in the speed accuracy trade-off. And then they proposed 4 different variants. So you see that the difference between the variants is the number of blocks that they use for each stage, and also the number of channels. So as we go from S1 to S4, I have more channels, and I also have more resolution. Instead of 224, I have 256. And for all the variants, they use R to be 1 divided by 4.67, around 20%. And also the expansion ratio is 2. And that means in the feed-forward network, this denoted by this green ones here, it uses an MLP that multiplies the number of channels by 2. So okay, that was the general idea behind this SHViT. Now let's just see some results. The first one is for the S1 variant that tries to compare it with other models that they were originally proposed for mobile devices, because they are very efficient and fast, but they are not as accurate as the others. So you can see that GPU throughput is around 3 times faster than the previous state of the art, while maintaining the same accuracy. So that's kind of impressive. And you see that for the CPU, they are reporting 2 things. One in the middle is the CPU, the other one is CPU ONNX. And this ONNX stands for Open Neural Network Exchange, that makes the models to perform faster on the CPU because they use the hardware accelerations that some of the GPUs are currently have, or use the parallelizations of the CPUs. So use it if you can, if you want to use it on the CPU, because you see that for some cases it is up to 10 times faster. For other models, it is like around 2 or 3 times faster. And then for the S2 variant, we can see that they have compared that with efficient former version 2 from ICCV 2023. So it's not efficient anymore, I guess. That you see it's on GPU, it is around 10 times faster, while it also achieves higher accuracy. But comparing with the other state of the art, which is MobileNet version 3 large, you see that it's still around twice faster while maintaining the same accuracy. And for the S3 variant, they compared it with FastViT. Apparently it's not fast anymore, that it is around 4 times faster than that. It has a better accuracy. And now again, comparing to the state of the art, which was Mobile One S2, you can see that it's around twice faster while maintaining the same accuracy again. And finally, the S4 variant, which was the heaviest one, you can see that even the heaviest one, if you use ONNX on CPU, it is in real time, 509 images per second. That's quite impressive. And you can see that it's again around 3 times faster than the state of the art while maintaining the same accuracy. And we can also increase the resolution from 256 to 384 or 512 and increase the accuracy even more. That on the last row, you can see that it is 82% top 1 accuracy. And on CPU with ONNX, it is still real time. That's quite impressive. And the final thing just to mention is this figure that compares the throughput on the x-axis and accuracy on the y-axis. That you can see SHViT, the yellow one, beats all the others in this trade-off. So yeah, that was all I wanted you to know about this paper. If you have enjoyed watching it, don't forget to like and subscribe. And until the next video, goodbye.